Question, which is Simon Billinge. He is coming from the Department of Physics and Applied Mathematics at Columbia University in New York, and also from Condensed Matter Physics and Material Science Department at Brookhaven National Laboratory. It seems appropriate for someone working on pair distribution function to come from two places. Simon has been in this field for a long time, and for me he is simply Mr. PDF. He has also written a book on PDF, and it's a privilege that we have the master of PDF telling us all about the functions. Simon.
Okay, so thank you very much, and it's really a great pleasure to be here. I talked to Bill a long time ago when they were hatching this in 2005, 6, whenever it was, and I was very excited about the possibility. These Irichi schools are almost mythical in the crystallographic community, and the opportunity to come to one was something I couldn't miss, and it certainly kept up to all the expectations. I've had a great time talking to people, all the students, so hopefully you too, and then today is sunny even. So how about that? Now, in the electron diffraction part of the course, I think they've been in nano land all week, but here we haven't had so much nano, so I thought I'd actually begin with a little introduction to nano. So nano goes back to ancient times. Nanotechnology was used in all the way back thousands of years without people knowing it, but it kind of people became aware of it in a way in 1959, when Richard Feynman gave his amazing lecture. So it was December 29th, 1959. And this is often shown as the beginning of nanotechnology. Many people haven't read this, but it's actually there. It's on the Caltech libraries, and they gave it a really great name, 1960 Bottom. So if you want to read this, go to 1960 Bottom. And then around 2000, President Clinton in the US announced National Nanotechnology Initiative and similar initiatives in Europe. So in 2000, it really took off. So that was 40 years later. So it's actually really interesting to go back and read this thing that Feynman wrote. So he was talking about writing Encyclopedia Britannica on the head of a pin. Of course, he got it wrong. It should be Wikipedia on the head of a pin. But he says, if we had something written in such a way we could read it using techniques in common use today, we'd press the metal into a plastic material, make a mold of it, then peel the plastic up very carefully, evaporate silica into the plastic to get a very thin film, shadow it by evaporating gold at an angle against the silica so all the little letters will appear clearly, dissolve the plastic away from the silica film, and then look at it through an electron microscope. He kind of got it right? That was 1960. He thought about making a small computer. How can we make such a device? What kind of manufacturing process would we use? One possibility we might consider, since we've talked about writing by putting atoms down, blah, 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 would be to evaporate the material, evaporate the insulator next to it, then for the next layer, evaporate another position of a wire, another insulator, and so on. So you simply evaporate until you have a block of stuff which has the elements, coils, and condensers of exceedingly fine dimensions. So I want to put this in perspective. This is Richard Feynman talking in 1960, and in 1960, computers looked like this. That's the context he was saying that in. It's really amazing how much vision he had. In 1960, cars looked like this. So, and hair looked like this. So actually, this is the very great physicist Lev Landau, but I love Lev, but I'm not sure I'd use his hairdresser. Okay, so nano is obviously small. It's the length scale, 1/1000th of a meter. But it's also huge. This is a slightly old slide, and it's, in terms of dollars, it's jigger. It's $1 billion, and now it's tens of billions of dollars, and getting towards hundreds of billions of dollars. But nanoscience has a big secret, which I call the nanostructure problem. So let's look at that in a bit more detail. So we're all crystallographers here, so we know what the crystal structure problem is. And basically, the crystal structure problem is this. So you're a chemist, you made a crystal, here's a crystal. What's its structure? Where are the atoms? So I want to propose a solution to the crystal structure problem. So here's my proposed solution. you give it to your grad student, and she puts it on the X-ray machine and pushes a button, and the machine tells her the structure, and then she tells you the structure, and then you write a paper. So this is a statement that crystallography is largely a solved problem. So I get into real trouble saying this in front of this audience, of course, because people are making a career out of crystallography, and they don't want to be told that they're making a career out of a solved problem. But the point is that often this works, that you can actually use this solution and you arrive at a crystal structure, and it's an incredibly powerful technique, but it's quite mature in some sense. It doesn't always work, of course, so sometimes the machine gets stuck, doesn't tell you the structure, and in that case, either you throw away the crystal or you make it the subject of the student's thesis to solve it. I should have added on here, or you do structure solution from powder, I guess, but okay, so all right, so let's say that instead of a crystal, you have a nanoparticle like this. What do you do? So you're a chemist, and it's the same thing, right? Here's a nanoparticle. I made it. What's its structure? Where are the atoms? All right, well, we like to reuse things in science, so let's try the same solution. So I give this nanoparticle to my grad student. She puts it on the X-ray machine, pushes a button. Well, if I gave her one nanoparticle, and even if she didn't drop it, there would be no signal coming out of the X-ray machine at all, because the Thomson scattering cross-section is 10 to the minus 26, and you need something like 10 to the 20 atoms to get a signal out if you have 10 to the 4 photons going in. So you just know from the math that you put a single nanoparticle in, nothing will come out. But let's say that you put a lot of nanoparticles in, you put them in a capillary, then what actually comes out is a diffraction pattern that looks like this. It has peaks in it. The peaks are broad and diffuse. But the machine certainly doesn't tell you the structure. So on the nanoscale, crystallography breaks down. We can't use crystallography. So there's this whole gigabillion-dollar industry that's being built on something where we don't even know how to solve the structure. So obviously, people are very interested in this. They're working on it. And roughly speaking, you could go about it in 3 different ways, actually more than this. But one of them is you could try and develop single nanocrystallography. That's like single crystallography on nanocrystals. You can, of course, use TM electron diffraction. I put that in because of our colleagues over the road there. And in analogy with what we do here, you can do polynanocrystallinity or powder nanocrystallinity. So we're going to explore these just briefly. So there's 2 ways to solve the nanostructure problem using crystallography. One way is the way they do it in proteins. So actually, protein crystallographers are actually solving the nanostructure problem, because what they want to know is the internal structure of the protein. The protein is a nanoparticle. The way they do it is they take copies of the proteins and they make them into a periodically arranged, orientationally ordered array called a crystal, and then they use the amazingly powerful crystallography to solve it. You can take that idea one step further and say, can we do that with inorganic nanocrystals and solve their structure? And the answer is actually yes. So this is Kornberg's group at Stanford in 2007. They did exactly that. They took 102 atom gold clusters, passivated with ligands on the surface, and they crystallized it. And the interesting thing was they solved it with protein crystallography methods, because it's like a little inorganic protein. And what they found was that it was a really non-trivial structure. It wasn't a little piece of FCC gold, but it was enantiomeric. It had chirality. It had low symmetry. It was an incredibly unique structure, very interesting structure. So that tells you that it's actually worth solving the nanostructure problem, that if you make gold very small, it's not just a little piece of bulk gold. So that's one approach to solve it using single crystal techniques. Another approach is actually you can take a single nanoparticle and you can try and solve the structure using single crystal type methods, and a lot of progress has been made in this regard. What I'm showing here is some work of Jim Zhuo, which was published in Science in 2003, actually, where he's using some phase retrieval method to look at not a crystalline, but a single nanoparticle. In fact, in this case, it was a double-walled carbon nanotube. And this is the image he reconstructed. This is just some kind of guess at what the structure is. It's not hard to guess it because it's a double-walled carbon nanotube. This isn't a structure solution, it turns out. This is an image. So to get a structure solution, you need to take different orientations you need to get this image in different orientations, and then you need to reconstruct it tomographically, and people are working on that too. But that's another approach, and you have to use electrons because then you have a much stronger interaction. You can see individual nanoparticles. If you have an extremely intense X-ray source, you can also do it with X-rays, and this is where the X-ray free electron lasers come in. And John Wright showed some beautiful work that John Spence published recently in his talk. This is a picture from John Spence when they were putting it together. And in this case, what you do is you essentially put your nanoparticles into droplets. You put them through a nozzle. You fire them this way. The beam comes this way. And you get multiple shots of randomly oriented nanoparticles. And then you use very clever algorithms to reconstruct them using computing. So they've managed to solve, they've got low-resolution images of viruses now, and they've got fairly low-resolution structure solutions from nanocrystals, but they haven't managed to get a single nanoparticle structure solution. Okay, but that's not why we're here. We're here because we're interested in powders. So powders are, we always tend to apologize in the powder community. We always say, well, if you have a single crystal, yeah, you should use single crystal. But actually, sometimes powder can be really powerful, sometimes it can even be better. So that's probably also the case in the nano world. So these are crystalline powders, these pictures, they're just kind of eye candy, really. But if we have lots of nanoparticles, we can put them in a capillary and we can do a powder diffraction experiment, and then what can we learn? And that's where PDF comes in. The other thing about powder data is that you can actually do material science. So if we can solve the nanostructure problem for powders, we can look at in situ situations. We can look at things like these are nanostructured electrodes in a PEM fuel cell. This is a nanostructured layer of nanoparticles in a photovoltaic. So we can do in situ, and we can do real time, and all the things we've heard about this week. But we'd like to do them on nanoparticles because a lot of the things we're interested in are nanostructured like this. If you tried to put one of these things in the X-ray free electron laser, it would simply bore a hole in it. Okay. Okay, so back to the nanostructure problem. So remember, we put nanoparticles on the machine, and this came out. So because it's a school, I want to go into a little bit this thing about the diffuse scattering. So this is actually a little simulation that Thomas Proffen put together when he was working in my group back in the late 90s. And basically, he was using his Discus program. And what we did is we made a simulation of a square crystal, and then we made 30% of the atoms yellow. And on the left, we arranged them randomly, or pseudo-randomly. And on the right, we put in some kind of short-range clustering component. And if you look at this, you can clearly see the difference between these two. And that's because your eye is a very highly developed